So part two, what if the indeterminate was in the form of 0 times infinity or infinity minus infinity? Then we're going to try converting to a fraction to get our 0 over 0 or our infinity over infinity, so we can use L'Hopital's rule. So here, for example, we have the limit as x approaches infinity. So here we would have, well, let's see, this would be 0 because we're going to get a very small value. We're going to approach 0. And this is going to infinity. So that's this situation. So what we probably want to do here is let's write this e to the negative x and put that in the denominator. So now we have infinity over infinity. And then we can use L'Hopital's rule. The derivative of e to the x is e to the x. The derivative of the square root of x, as I asked you to memorize, will be 1 over 2 times the square root of x. And if we apply, wait a minute, take this 2 times the square root of x, and let's move that to the denominator, because that's basically what's happening here. 1 divided by 2 times the square root of x divided by e to the x. That puts everything inside of one denominator, if you will. And so now here we have infinity times infinity, which means this is 1 over infinity, so we're going to 0 for that limit. We're done. If we had, well, careful, approaching 0 from the right, the limit as x approaches 0 from the right of x times the natural log of x, this would be 0. And this would be approaching negative infinity if you think about that natural log curve. All right, so we're going to change this x to 1 over 1 over x. All right. So that puts x in the denominator as a fraction. Okay, think about this for a second. It's still the same thing. We don't divide by fractions. We multiply by its reciprocal. So you have your x being multiplied to the natural log of x. But, and now, this gives us a negative infinity over infinity. So we can now use L'Hopital's rule. So the derivative of natural log of x is 1 over x. This would be, if you would, x to the negative 1 power. So that derivative is going to be negative 1 times x to the negative 2 power. And then rewriting x to the negative 2 power as x squared in the denominator, we can say, oh, like we did up here, multiply by the reciprocal because you don't want to divide by fractions. So that becomes 1 over x times x squared over negative 1. And now we can do some canceling here. And that just becomes negative x. And as we approach it from the right, going into 0, that's 0, because we had that over here earlier. As the limit as x approaches 0 from the right of that, x was giving us 0. All right, the limit, wait a minute. Again, approaching 1 from the right, we have the natural log. So I think I'm going to bring in some graph here, because I think we're going to be working with this natural log graph quite a bit here. All right, so let's see, what do we get here? So as x approaches 1 from the right, we're approaching a very, very small value. And as x approaches from the right here, that'd be 1 over 1.001. That's going to be really small. So this would be infinity minus infinity. So we're going to convert this to a fraction. So we're going to add, or technically subtract these two together by getting a LCD here. So that x minus 1 is multiplied to this one. Natural log of x is multiplied to that one. And now this gives me the form 0 over 0. Okay, so as my natural log, if we look at just the top here, that's approaching 0. This is approaching close to 0. So 0 minus 0 is 0. 0 times 0, 0. we can use L'Hopital's rule. The downside, you're going to have to do the product rule here on the bottom. The derivative of x is 1, the derivative of 1 is 0, the derivative of natural log of x is 1 over x. So that's 1 minus, that's this minus sign, 1 over x. On the bottom, okay, I chose to do the derivative of the first function, 1 over x times the binomial x minus 1, plus now the derivative of the second function, 1 times the natural log of x. Well, since there's an x in the two individual fractions up here, I'm going to multiply top and bottom by x to cancel out the fractions within the fraction. So the top becomes x minus 1. This is just going to cancel out and become x minus 1 plus an x times the natural log of x. And again, we're approaching from the right. This is still a 0 over 0 situation. So L'Hopital's rule one more time. The derivative of the top will be 1. On the bottom, the derivative of x is 1. Well, that's going to be a 0. Plus, okay, x times natural log of x, that'll be another product rule. So the derivative of x is 1 times the second function, natural log of x, plus x times the derivative of natural log of x, which is 1 over x. Well, those are going to cancel out. That's going to leave me a plus 1. So this will be, this 1 plus that 1 will give me a 2 plus the natural log of x. Now we said that, again, as x approaches 1 from the right, that would be approaching a 0. So this natural log of x for the limit becomes 0, and this now becomes 1/2, and there's my limit value. All right, okay, to the next one. The limit as x approaches infinity. So here we have another infinity minus infinity. We want to convert this to a fraction with your, wait a minute, no, we can't turn that into a fraction. We're going to rewrite this as a product by factoring. So what I'm going to do is I'm factoring out the x to the front. Now wait a minute, there's no x here. It's in the exponent, but I can't factor it out of there. So I'm going to treat this like x e to the x over x. So that's why this x is in the denominator here. So now I have infinity times infinity over infinity minus 1. So that's infinity times infinity, which equals infinity. And we're done. We found the limit. We did not have to use any L'Hopital's rules here. All right, indeterminate powers. Sometimes you're going to have functions raised to the power of a function. All right, so when that happens, when you approach your x value to a, your f of x and your g of x can run into 3 possible types. Your f of x approaches 0, your g of x approaches 0, and now you're looking at 0 to the 0 power. Your f of x can approach infinity, your g of x can approach 0, so you have infinity to the 0 power. F of x can approach 1, g of x can approach either of my infinities, so you have 1 over infinity. So each of these 3 cases can be treated either by taking the natural log of both sides. All right, so if I had y equals f of x to the g of x, and I take the natural log of both sides, this is very beneficial because then taking the natural log of the right side allows me to take this exponent and move it to the front of the natural log, and we can work with it from here. Or you can write the function as an exponential. F of x to the g of x is equal to e to the g of x times the natural log of f of x. All right, 2 possible ways of writing this. All right, so both these methods were used in differentiating such functions. In either method, we are led to the indeterminate product of g of x times the natural log of f of x. As you can see, it's either in the exponent or it's in here in the first one as well. And these are would be a 0 times infinity situation. So looking at an example here, Here we have our function, 1 plus sine of 4x, all raised to another function, cotangent of x. All right, so again, you're going to need some space to write here, so be sparing with your space so you can use a lot of it. So as x approaches 0 to, from the right, for the base function, that's our f of x, that's going to approach 1. Sine of 4 times 0, well, sine of 0 is 0, so that's a 1. And cotangent of x as we go to 0, cotangent, that's going to have an asymptote at 0, and approaching it from the right means we're going to go up to a positive infinity. So we're looking at a situation of 1 raised to the power of infinity. Okay, so we need to use this method here. We're going to take y and let that be our function right here, function raised to a function power, and we're going to take the natural log of both sides. So what that does is that moves cotangent of x out to the front multiplied to the natural log of both sides. So now what do we do? Well, let's see. Cotangent of x, we don't want it something times. We want to create a fraction so we can get that indeterminate form. So the reciprocal of cotangent of x is tangent of x. So we put that in the denominator. Cotangent of x is equal to 1 over tangent x. Multiplying it to your natural log puts tangent x in the bottom. So this is a 0 over 0 situation when my limit is approaching 0 from the right. So that means we can use L'Hopital's rule to the right-hand side. So the derivative of the natural log of 1 plus sine of 4x all over the derivative of tangent of x. Well, I'll do the difficult one. Tangent of x is just secant squared x. The top, here we go. This is where, if you recall from the test we worked on last, we had that chain rule for the natural log. It's 1 over what's ever in the argument of the natural log. So that's this part. And on the top is going to be u prime, the derivative of the inside. So the derivative of sine is cosine of 4x, and then the derivative of the inside of the cos of the sine function is going to be 4. That's multiplied on the top. All right, so now as we approach 0, secant squared going towards 0, that's going to be a 1, because again, think of this as 1 over cosine. Cosine of 0 is 1. Well, that's right. Cosine of 0 is 1. That's 4. Cosine of 0 we said was 0, so 1 plus 0 is 1. So 4 over 1 is 4. All right, now but we're not done. All right, because we have, remember, we also found that we are taking the limit as x approaches 0 of the natural log of y. So we've only found the limit of the natural log of y, not the limit of y. So here's what we're going to do. Now you take base e to both sides. So the limit as x approaches 0 to infinity of e to the natural log of y, well, that's going to be a good thing. E to the natural log will cancel each other out to be y, is equal to e to the fourth. So the limit as x approaches 0 from the right of y, remember we let y represent our entire function raised to a function, is equal to e to the fourth. Number one error is forgetting to do this last step. All right, calculate. Oh my lord. As x approaches 0 from the right of x to the x power. That's 0 to the 0. Again, take the natural log of both sides. That's going to move that x out to the front. So the limit as x approaches 0 from the right of the natural log of y, remember, we're going to have to clean this up at the end. So now we have the limit on the right side of x times the natural log of x. Wait a minute, we did that one already. That was 2b, and we got a 0 for that answer. So let's just steal this work and use it here. But again, we're not done. We have to say the limit as x approaches 0 from the right of y. So we got to get rid of the natural log, so we take base e of both sides. Again, e to the natural log cancels out. E to the 0 is 1, and we found our limit. And this problem's done. All right, so that wraps up that section. We'll see you for the next one.